this is activity 8C from about satellite motion from the level 3 ESA physics textbook. Question 1. Two ships, mass 6,500 tons, 7,500 tons, are 58 meters apart on the surface of the sea. Calculate the gravitational force between them. So, the first ship, we'll call it N1. We could call it, it's got a mass of 6,500 tons. Now, a ton is 1,000 kilograms, so that's 650,000 kilograms. N2 is a mass of 7,500 tons, or 7.5 million kilograms. The formula is F equals capital G, and they do it as little m like that. You can just use any two m's really. M1, M2 is how I learned it when I was younger. So we're going to put the two masses in here and the distance between them in here and the gravitational constant in there. And the gravitational constant G is given to us as 6.67 times 10 to the minus 11, and that's if you've got masses in kilograms. And we've got R in this case is given as 58 meters for these two ships. So F equals 6.67 times 10 to the minus 11. We're going to do a quick conversion of these into scientific form. We're going to move the decimal point 1, 2, 3, 4, 5, 6 spaces to put it here. So times 6.5 times 10 to the 6 times, do the same thing to this one, 7.5 times 10 to the 6, all divided by 58 squared. Now you can do that. The whole point of putting this into scientific form is we can do the numbers separately from the powers of 10, from the exponents. So we'll do the numbers first. We do 6.67. I'm just going to actually write it on here to make it more obvious. And the reason we want to do that is that these ones here can be done super easy. That's actually because the exponents, it's actually an addition subtraction thing. So 6 plus 6 is 12, minus 11 is 10. So we'll do that side of it is times 10. 58 squared is 3,364. And 6.67 times 6.5 times 7.5 is 325.1625. So multiply that by 10, divide the whole thing by 3,364, and we get that the force, the gravitational force between these two ships is 0.9666 newtons, or 0.97 newtons to two significant figures, which is very small. That's the equivalent of about the weight force of a 100 gram item. Given that these ships weigh an enormous amount, that's not going to have very much effect. What other force acts to prevent the gravitational force from causing the ships to move each together? I think this is a bit of an odd question, because the force that we're looking for is probably friction between each ship and the sea. But the problem with that is that friction only acts once you're moving. Two objects don't need very much force at all, and at dead calm sea, even theoretically, even 1 Newton would be enough to slowly pull these ships toward each other. So I don't particularly like that question, but that's definitely what we're going to be being asked for. Calculate the gravitational force between the heavier ship and the Earth. Well, for this, it's at the surface of the Earth, and that all boils it down, right? So for this, we can just use F equals mg, we don't need to go through this whole calculation. And if we're using g is 9.8, or we can use g as 9.8. So 9.81 if we want it to 3 decimal places, 9.8. Well, we use 9.8 because it's what the ballpoint system is for now. Later on, when we do the exam, we're going to have g to 3 significant figures, not just 2. So keep that in mind. Which the heavier ship is 7,500 tons. So times 9.8. So that's going to equal 73,500,000 newtons, or 7.35 times 10 to the 7 newtons. I've got one significant figure extra there than I probably should have. If so, it rounds up to 7.4 times 10 to the 7 newtons. So two significant figures. And part D. What other force acts to prevent the gravitational force from causing the ship to move toward the centre of the Earth? Well, what supports the ship? And this is buoyancy, force due to displacement of water. So basically, if you can think of buoyancy in loads of different ways. But one way to think of it, if we had done any work on pressure, which we probably have not with you, would be that at the surface of the water there is no water pressure. As you go deeper in the water there is more pressure, and pressure exerts a force onto the hull of the ship to keep the ship up. Overall, this can be considered buoyancy due to displacement. Hence the way I've framed it there. Alright, question 2. Communication satellites are usually placed in orbit at a height where they remain fixed above one point on the Earth's surface. Well, this has just generally been true. This is probably less true today. If you're following the news, you'll see that they're launching constantly. Sorry, you probably haven't been able to hear me because my microphone's not been very well set. So good luck. What I was going to say on this is that geostationary. So question 2, communication satellites being in geostationary orbit was definitely true some time ago, and for example TV transmitting satellites are often in geostationary orbit. The problem is that puts them very, very far up, which means that even the speed of light for transmission comes into play, so any two-way type communication is relatively slow. The problem, and so this is starting to become an issue for certain types of things, particularly for things like internet. And as a consequence of that, we're seeing people propose so-called constellations of thousands of small satellites in very low Earth orbit, which will unfortunately also mean thousands of little bright specks passing across the night sky. But anyway, we're doing a thing on geostationary satellites, so let's look at that. It says, part A, calculate the radius of the satellite's orbit. There's a classic case of looking at what we're given. So we're given here that the height above the Earth's surface is, so 3.59 times 10 to the 7 above surface, and we were also given that the radius of the Earth is 6.37 times 10 to the 6 meters. So our radius of orbit, so we've got this has got a radius of the Earth, and then you've got this height above the surface to the satellite. So radius of the orbit equals r plus h equals 3.59 times 10 to the 7 plus 6.37 times 10 to the 6, which is, now this is, you can't just
like go add those two numbers together, you've got to do this with the exponents, or put the two exponents to be the same. So here we could, for example, make this 0.637 times 10 to the 7, and then add that to that. So that would be fine too. So 3.59 plus 0.637 gives us 4.227 times 10 to the 7 meters. All right, part B. What are explain why the period of the satellite's motion is 8.64 times 10 to the 4 seconds. Well, if the satellite is geostationary, this means that it orbits the Earth synchronized to the Earth's rotation. So if we say that the Earth rotates every 24 hours, for example, then that's going to tell us how long the period of rotation of the Earth is, which tells us the orbit of the satellite, or the period of the orbit of the satellite. So Earth rotates 24 hours, therefore period equals 24 times, so it's 24 hours times 60 minutes times 60 seconds, which is 8.64, and so it's 24 times 3600, which is about 86,000, it is not about, it's 86,400 seconds, or 8.64 times 10 to the 4 seconds. Now I do wonder whether that's entirely, well, no, I guess it's definitely true, is it? Yeah, that's got to be true. I was thinking about something about the way the Earth goes around the sun and stuff, but one way or another, the satellite has to be overhead still all the time. So if the Earth goes around in that period, then so does it. The question is, does the Earth actually rotate once every 24 hours, or does it actually rotate once every 24 hours, plus or minus a little bit, because the Earth, of course, goes around the sun once a year as well. But I think it might all be dependent on your reference frame. So let's just leave it at this. C, calculate the speed of the satellite. Well, if it goes around the Earth, if it goes around its orbit every 86,400 seconds, and we've now got a radius for its orbit. So firstly, we need to know we're going to use this formula, velocity equals distance over time. How far does it go? How much time equals the velocity, or its speed, at least speed equals distance over time. Velocity, of course, would be a vector, and after you've gone around the orbit, you're where you started, so the overall or average velocity could be considered 0. But here we're talking about the speed. So what we want is the distance. Well, in this case, the circumference equals 2 pi r. The circumference of a circle equals pi times the diameter of the circle. Now the diameter of the circle equals twice the radius, so the circumference equals 2 pi r. We'll go for 6.28, that's 2 pi, times 4.227 times 10 to the 7. And the time equals 1 period, which is 8.64 times 10 to the 4. So this is 6.28 times 4.227 times 10 to the 7, all divided by 8.64 times 10 to the 4, and it gives us 3,072.4 meters per second. That's pretty fast. That's 3 times the speed of sound. Or 3,100 meters per second to 2 significant figures. Although we've been given 3 significant figures, so we actually should be 3,070 meters per second to 3 significant figures. Okay, and part D, calculate the acceleration of the satellite. Okay, we got potentially 2 ways we can do acceleration of the satellite. We could probably look at its force using this one. Actually, we can't. Why can't we? Because we don't know the mass of the satellite, so we can't use that. Or, but we can use this. We can use AC equals V squared over R. Okay, so we 3072.4 squared all over the radius, which we had up here, 4.227 times 10 to the 7. So let's do that. So square that. 4.227 exponent 7. This is a classic example, making sure you use the exponent button here, or brackets, don't just plug it in. And you should get, or I get 0.223 meters per second squared, which shows that the gravity way out there is pretty low, because this force, this centripetal acceleration, is going to be provided by gravity. And I guess if we look at the radius here, this radius of its orbit is much greater by a factor nearly of 10 than the radius of the Earth. So we should expect gravitational force that's going to be, somewhere around 100th of that on, because from this formula it would be proportional to 1 over r squared. So we expect the gravitational force to be somewhere in terms of orders of magnitude around 100th of that on Earth. This is 200ths, so that's about right. Means we're in the ballpark anyway. What is the nature of the force that causes the acceleration? It is the gravitational attraction between the Earth and the satellite, i.e. the weight force. And of course, that attraction acts on the Earth and on the satellite, but the Earth is so much bigger than the satellite, it has negligible impact on the Earth. Just do my quick checks. Yep, those answers are all accurate. All right, question 3. The Moon has a mass of 7.36 times 10 to the 22 kilograms, orbits the Earth every 27 days with an approximately circular path. So we're talking about the Moon here. Show that the speed of the Moon in its orbit around the Earth is 1,040 meters per second. Well, we want to use, speed. So what's speed? Speed is distance per time. The distance traveled divided by the time it takes to travel it. The distance here, it's a circular path, so the distance is going to be 2 times pi times whatever radius of the path is. And we've been given that the Earth's approximately circular the Earth travels an approximately circular path with a radius of 3.84 times 10 to the 8. So 2 times 3.14 times 3.84 times 10 to the power of 8, which is 6.28 times 3.84. 24.1152 times 10 to the 8, or 2.41152 times 10 to the power of 9. I'm going to keep all those digits for now because I'm going to do this division soon. And the time we've been given as, and they see it every 27 days. They've actually given us the time in seconds, so I don't need to do the calculation to work that out. So the speed equals 2.41152 times 10 to the 9 divided by 2.33 times 10 to the 6. Now we can do this bit separately. That'll give us 10 to the 3. And we do this bit at the front here, 2.41152, 2.33, 1.035 times 10 to the 3 meters per second, which means that, by the way, that the Earth is traveling around at around what would be the speed of sound on Earth at ground level, but makes no. It's not the speed of sound in space because there's no sound in space, so it's not really that important. Show that the centripetal force keeping the Moon in its orbit is 2.04 times 10 to the 20. Well, let's have a look. Centripetal force. What's your equation? Fc equals mv squared over r. What's got a mass of the Moon here somewhere? 7.36 times 10 to the 22. That's the mass of the Moon. Whoops. Times the v, the velocity, 1.035 times 10 to the 3. Now remember, I've got to put the squared in the right place here. Squared, all divided by the radius, which we used up here, 3.84 times 10 to the 8. So we do this calculation. Again, I'm going to do the numbers separately. 7.36 times 1.035 squared over 3.84. And then I'm going to do the tens, 10 to the 22, 10 to the 3 times 10 to the 2, 10 to the 3 squared is 10 to the 6. Sorry, it's the equivalent of 10 to the 3 times 10 to the 3, which means we add up the powers, all over 10 to the 8. Let's do this one over here first. 22 plus 6 is 28, divided by 8 is 10 to the 20. Sorry, 10 to the 22 times 10 to the 6 is 10 to the 28. 10 to the 28 divided by 10 to the 8 is 10 to the 20. So you add the multiplieds, add the exponents of the two that are multiplied together, and subtract the exponent of the one when you're dividing. And the numbers over here, 7.36 times 1.035 divided by 3.84, we get 2.053. That's an extra significant figure, so now we round. 2.05 times 10 to the 20. What are we looking for? Newtons. It's pretty high, isn't it? And really what you'll see is that that's created by the really large mass of the Moon. That's been the key to it. The key to working that out anyway. And ultimately that force is generated by the mass of the Earth and Moon. We've been asked to calculate now the mass of the Earth. So, mass of the Earth. How are we going to find that? Well, we need a formula. So, we've got the mass of the Moon. We know a gravitational constant. We know a radius and so on. The formula we want to hunt for ultimately is F, and we know a force. Well, the key idea here is that the centripetal force equals the weight force. Because it's the weight force pulling down on the Moon, pulling it toward the center of the Earth, that is creating that centripetal acceleration that is pulling the Moon in a circular path. Okay? So the reason the Moon goes in the circular path is because of its weight force, which is also its centripetal force. So the weight force is the force that causes the curve. So F equals G m over r squared. And we know the force, 2.05 times 10 to the 20. We know we know G, it's the universal gravitational constant. 6.67 times 10 to the minus 11. We know the mass of the moon. We've been given it here. 7.36 times 10 to the 22. We don't know the mass of the Earth. Let's just call it M. Or might as well call it ME. And we know the radius between the two because we worked it out. We got given it actually. The radius of the moon's orbit. There it is. 3.84 times 10 to the 8 squared. And now we're going to have to do some calculation and substitution. I'm going to do this side of the calculation first. So we're going to go to 2.05 times 10 to the 20 equals something times ME. 6.67 exponents negative 11 times 7.36 exponents 22. And that gives me 4.90912 exponents 12. And then I'm going to divide that by 3.84 exponents 8 squared equals, and I get 3.3, and I've got this in, it's actually 3.33, and times 10 to the negative 1, 2, 3, 4, 5. Right, that's what I'm getting. And so therefore ME equals 2.05 times 10 to the 20. This is a classic case of where I would double check my calculations by trying to do the arithmetic another way, because you never know with something like this whether you're going to make a mistake, and so I'd probably try it with brackets and things in it just to make sure my calculator is not doing anything dumb. And I get that the mass of the Earth equals 6.825 times 10 to the 15 kilograms. It's not large enough. So I definitely did something wrong here. You know what I did wrong? See this times? That should have been a divided by to start with. So let's get rid of that. How did I know I got it wrong? Well, because it actually gave you the mass of the Earth in the table on the previous page. So you could check there too. It's really a show that question when you've already been provided it, isn't it? 20 equals divided by 3.33 exponents negative 5. This time I get 6.156 times 10 to the 24, which is closer to the mass of the Earth. It's still not quite on the money. I wonder if I just did a few things wrong, like some subtle arithmetic. But let's just see what they put in their answer book. 6.17 times 10 to 24. So I suspect that something's gone astray in my roundings, maybe compared to that. But otherwise, it's close enough to the answer in the book for me. That's the method anyway. The centripetal force is produced by the weight force, by the gravity force, and the gravity force can be found using this formula. So you equate the gravity force of this formula to the centripetal force you found in this part of the question. All right. Question 4, moving along. A satellite is placed in orbit about the moon at a height of 55 kilometers above the surface. The moon, so this is of the moon, let's lose track of that. The moon has a radius of 1.7 times 10 to the 6 meters and a mass of 7.3 times 10 to the 22 kilograms. So it's another classic of they've given you an above the surface and a radius. Okay. What is the radius of the orbit of the satellite? Well, again, we've got this situation like we had in the first part of the first question. We've given this distance and we're given this distance. This was 5.5 times 10 to the 4. And this one is 1.7 times 10 to the 6. So interesting, isn't it? It's actually orbiting quite low. So the radius equals 5.5 times 10 to the 4 plus 1.7 times 10 to the 6, which is 1.755 times 10 to the 6. These are actually in the roundings on this other one, which is a bit annoying. I'm just going to leave it like that for now. It rounds to 1.8 times 10 to the 6 to two significant figures, but it sort of makes a nonsense of things. B. Show that the strength of gravity at the height of the orbit is 1.6 newtons per kilogram. So here we've got this idea of what happens if you apply a mass of 1 kilogram, if you think about 1 kilogram test mass, or what's the force per kilogram. And so the way to think about this, you can just, instead of having to remember a whole extra formula or anything, just imagine you've got your F equals, go away, F equals G m over r squared. Now we have the mass of the moon, we have G, we have the radius where the satellite is. We want to know the force per kilogram. So if we just apply little m equals 1 kg into this formula, we're going to get F, or in this case we call it little g actually. Little g, the gravitational field strength, i.e. the force acting on 1 kilogram. G equals force per kilogram, therefore the force acting on 1 kilogram. G equals capital G m over r squared, because this m here becomes 1. And we can now work that out. 6.67 times 10 to the negative 11. Always look it up, just double check it that you're transcribing it correctly. Times the mass of the moon, 7.3 times 10 to the 22. And then we're going to divide it by r squared. R 1.7 times 10 to the 6. Oh, that's not the radius, is it? The radius we want is this one we've been using. 1.755 times 10 to the 6 squared. And now we do this, and another opportunity to use your calculator. 6.67 exponents negative 11 times 7.3 exponents 22. I'm just going to do it in 2 steps to try and make it less likely that I'll make a mistake. 4.8691 times 10 to the 12, that is still there, that 9, divided by 3.08, and then there's a 0025, but those extra zeros are going to be pointless, I think. I'll just put them in for now anyway, times, you never know when they might muck the last rounding up, I guess. And notice the 12s here are going to cancel out, so we're going to get 4.8, so the 10 to the 12, 691, divided by 3.080025, oops, equals 1.58. 1.58, and it's newtons per kilogram, because it's a force per kilogram. Yep, that's what the whole idea is. Okay, now it's an interesting question, and maybe it's 1.6 newtons per kilogram to two significant figures. We have only been given two significant figures for the radius of the moon and the mass of the moon, so that's probably the right way to do it. Okay, part C. Show that the orbital speed is 1,700 meters per second. All right, so here we've got this idea again that the weight force is equal to the centripetal force Now, we haven't been given the mass of the satellite or anything, but if we put the two equations in, we'll get this. The weight force equals mg equals gmm over r squared, because this one is, and this one is that what I want to be done? I want the speed. Sorry, let's. Sorry, I put the other equation in here, didn't I? Duh. What I wanted here was not. Sorry, FC equals mv squared over r. That's the one I wanted. So, FW equals FC. We put in here mv squared over r. Well, these m's, we divide both sides by m, they cancel out. So G equals v squared over r. And therefore we can work out, if we rearrange this, we can substitute it and then rearrange. So 1.58 equals v squared divided by, what's the radius? The radius is up here again. 1.755 times 10 to the 6. V squared equals 1.58. 1.755 times 10 to the 6. V equals the square root of some number, and then we'll do it. 1.58 times 1.755 exponent 6 equals, so that gives me 2,772,900. We square root the answer, and we get 1,665 meters per second, or 1,700 meters per second, to two significant figures. Cool. I've run myself out of space here. I just clear the frame, calculate the period of the orbit. This is where having run myself out of space, I'm going to then struggle to get what I need back. What am I going to do? Maybe I just scrub for a bit. I want that and that, I think. Who cares? No, I'll keep it. I'll just work down the sides. I should have laid my work out better. So I'm just going to... And then I'm going to work in another color so that if I get too close, it's going to be obvious what I've done. So D. Part D. Calculate the period of the orbit. Now, the period equals how long it takes to go around once. So, that is the distance divided by the speed. And we get that V equals d over t. We rearrange. Multiply both sides by t. We get vt equals d. We want to get the t. We get t equals d over v, right? So that's the sequence to get us to here. So the period equals the distance 2 pi r divided by the velocity 1655, and it's 2 times 3.14 times 1.755 times 10 to the power of 6 divided by 1655. Another great piece of calculation to do. 2 times 3.14 times 1.755 exponent 6. I'm guessing that some people attempted, when they're doing these sorts of problems, to not use their calculator, but to use their computer, or maybe their... and I think if we just change this, we'll just round this to two significant figures. It should get 6,700 seconds, which is actually only 2 hours. So the period of the orbit of this satellite in a relatively low lunar orbit is just on 2 hours. Part E, if the height of the satellite is increased, explain what happens to its speed. Well, that's an interesting question, isn't it? Do they mean that if it stayed in orbit and we increased its, if we kept it in a circular orbit at a greater height, so if we same orbit? Like, still in orbit or not? So we can have a look at some of these and think, well, would it be at a greater speed or a lower speed in a higher orbit? Well, if we place it in a higher orbit, then the radius would be going up, which means that here the gravitational force would be going down by squares, yeah? Down by squares. And then the speed is based on the velocity squared divided by that. So, whoa, they didn't give us speed. Where did we get? Hang on, we got speed. Oh man. If it, I'm still a bit concerned that they're thinking that it's an orbit. If you actually increase the height of that satellite, like just pushing it outwards, then its speed would stay the same, but it would no longer be in its orbit, I suspect. In fact, it would probably fly away from the moon. I'm not sure which answer they want. If it is still in orbit, then, so in other words, a satellite orbiting at a higher orbit, it actually has a lower speed. Now, proving that is a case of running the formulas backwards. You could run a formula for a higher radius to do it, or you can just look at all of these formulas at once. So, for example, if we go over here, we've got that G equals V squared over R, but here we've got G is equal to GM over R squared. So GM over R squared equals V squared over R. Multiply both sides by R, you get V squared equals GM over R. And what that tells you, if these two are the same, then as you increase the radius, the velocity goes down. So increase the radius, this under part, then velocity goes down. Decrease the radius, velocity has to go up. This is the velocity for a stable orbit. But if you just raise the orbit, what happens? Well, then V is higher than the speed is higher than the orbit speed, than the orbital velocity, and satellite disappears. Actually, it doesn't, it just goes higher. And ultimately, because it goes higher, it has to lose energy and might slow down. So that will slow it down eventually as well, but it's a really complex dynamic. I don't think that's what they're really expecting. I think they're more expecting this first answer, that it's still in orbit at this higher frequency, a higher orbit, therefore it's going to have a lower speed. Let's have a look at what they had in mind. The speed of the satellite has an inverse relationship with the orbital radius. Yeah, they've given this exact derivation that I've given you. And so if the radius is increased, the speed will decrease. There you go. But if you just boost the orbit, remember it does actually start out, it has this extra speed still. How do you boost the orbit? Well, for that's tricky as well. Arguably, you've got to raise the speed to send it out of orbit. If you slow it down, it should fall. Confusing, not? Good luck with that. Ask me more if you've got questions.